Everyone. I have already shared a link in the chat for my robot, and today's session will actually just take place on the my robot itself. So I didn't really prepare, I didn't prepare any slides, but I prepared some information on the my robot, and then we will just be able to go through it and have maybe a little bit more of an interactive session. Last time you asked me to give you like a demo for neural networks, an additional demo. So I was hard at work and I built a little program that tries to utilize artificial neural networks to fulfill a task. And we can look at it together today. Just for the organizational part, we will have a short lunch break at 12 again for an hour. It might be that we will be a little bit faster today, so you can go into your well-deserved winter holidays. And we will see how long we take to get through the content that I've created for us today. All right, and I will just share my screen so that everybody who's watching at another time can also see what we are looking at. Yes. Cool. And we can just start with the top left here on the Miro board. I see that some are already on it. I didn't prepare a check-in this time. So we can just jump straight in. Don't worry, there are some interactive exercises as well. Just to give you a little bit more context here on the top left, we just start with chapter 1, introduction, and give you a short overview of where we stand, so to speak. So over the last couple of weeks and months, we have engaged with AI, or the technical part of AI, what AI means in the 21st century, basically, on a technical level, by first looking at Python, then data ingestion, data cleaning. You've all seen the slides in the previous rounds. And last session in the Engineering Rampup, we talked about artificial neural networks and how to train them. Maybe some of you have finished the exercises on data camp that you didn't finish until last time for today. And we should all be set to engage in a more deeper dive in artificial neural networks today. And on Tuesday, there was a nice workshop from Fabian for AI infrastructure. So you already have maybe some insights into what kind of infrastructure you need in order to train and run your models. Just as a context for you, in the more technical part of the KT Plus program, the next workshops will be the handling of pre-trained models workshop, also given by Fabian, and the fine-tuning workshop given by Fabian and me together. And those will happen in February. And even if you're starting your coding adventure with the 1st of January, you can still come in these workshops and get a little bit more information about these topics. And actually fine-tuning, even though this workshop will take place in February, will also play a role in today's workshop. So if you don't understand everything today, don't worry, there will be a more detailed explanation of what fine-tuning is and how you can use it in your own projects in the next year. Okay, yeah, let's continue with the next slide, so to speak. So where do we stand in terms of depth today? So even though for most of you this will be the last day of working this year, we will still do a deep dive in terms of content today. So if we imagine the topic of AI to be an iceberg, we will be true and sound below the waters in terms of depth today. So I know like this like some of the things that we will talk about today might be a little bit complex, but if you don't understand everything, then just feel free to ask in the chat, or maybe like write a sticky note on the Miro board as well, and we can go into a little bit more detail. But if you go out of this workshop today and you feel like you only understood like 60% or something like this, then don't worry. This is very much not the intention, but this is very much accepted in today's session, because yeah, the topic just is inherently a little bit more complex compared to building basic Python functions, for example. But nevertheless, this shouldn't deter us from still wanting to learn and taking away the things that we would like to learn today. And maybe for some of you, this is actually not that complex, and you can just like take this away and immediately utilize this into in one of your projects. So yeah. I mean, like we will not reach the deeps of depths today, and indeed we will not reach this in any of the workshops. But still, today is a little bit more complex than what we had last session. So yeah, keeping in the true fashion of just ever increasing difficulty in our workshops. All right. Then I have prepared a short poll, so to speak, with you, and maybe as a short introduction to today's workshop and why it might be relevant for you. And for this, I've prepared just like 3 answers, which all go into the direction of whether or not you want to build a chatbot for your use case. We know for the first round that there were many companies that wanted to build an internal chatbot, or maybe a chatbot that faces customers. And I will just open the voting here, and you have 1 vote to click on one of those 3 sticky notes here, where you can basically give me a short feedback whether or not you want to build a chatbot in your use case. And like the one on the left is we want to build a chatbot, and the one on the right is we do not plan to build a chatbot, and the one in the middle is we do not plan to build it right now, but maybe in the future this is a use case that we want to build. All right, I will open the voting, and you can choose one. You have 50 seconds for that. All right, looks like everybody has voted. Ah, I see. Nice. Okay, so actually the majority of you wants to build a chatbot, or you want to build a chatbot in the future. I don't think this comes as a big surprise, as like generative AI and large language models are the hot kid on the block. I don't know, the hot topic. And only 4 of those who voted said they didn't want to build a chatbot and do not plan on building one in the future. And for those of you who said they want to engage in some kind of chatbot, today's session might be of higher relevance, because it's all about building something with a large language model. But and I mean, of course, like when we talk about chatbots, we don't usually mean to just build an API or like a connection to ChatGPT or something like this. Usually we talk about it in the context of RAG, retrieval augmented generation. If you haven't heard the term before, don't worry, it's also going to be topic of a workshop that will be given in the next year. But on the following slide, I just want to give you a very short intuition about how retrieval augmented generation works from a technical perspective. What is the retrieval augmented part of retrieval augmented generation? This is basically that you enable your large language model or your chatbot to interact with documents that you have saved somewhere in your digital ecosystem. So you might want to build a chatbot that can retrieve data or sales data or data from your offers in your online shop, for example, and provide this to your customers. And for this, your chatbot needs to interface with all available items that customers could usually buy from your online web shop or something like this. Or maybe you want to build a chatbot for your internal use where your chatbot is there to find historical documents that might be hidden somewhere. For this, your chatbot then needs to interface with your legacy database or some centralized data storage where your chatbot can engage with the documents that have been placed there sometime. So how does this look like from a technical perspective? So when a user engages with a retrieval augmented generation system, they just put in a query into a text box or something like this, and the query is just a request, right? So it's a request for an action or for something that the user wants the system to retrieve for them or to generate for them. And this request, so this request here on the left side is like written in red. Here's a user request coming in as an example. Who is the person from supplier 12, from some supplier, who is responsible for the shipment 1337? So here the user is asking for very specific information that the retrieval augmented generation system is supposed to retrieve from some internal system. And then here on the very bottom right, the model then answers with some answer. So for example, supplier 12 is Jane Smith, or the person responsible is Jane Smith, and then follows up with a question, would you like to have the phone number or the email contact or something like this? And now let's take a look at what happens internally with this. So you may not be surprised that all of the processes that are going on within a retrieval augmented generation system somehow rely on large language models. But what you may not know is that it actually relies on two large language models that function in tandem, and that there are some other operations going on. So let's walk through it step by step. The first thing that happens when a user query comes in is that this user query gets passed to our first large language model. And this is a so-called encoder, large language model encoder. And everything that this network does is to transfer the query that comes in a natural language, and it processes the query and transfers it into a vector representation. So whenever we feed something into an artificial neural network, the output will be in a vector representation. We've looked at this in the last session that we did together. And this vector representation is just, so to speak, a computerized version of processing steps that have been applied to the input here. And this vector representation, if the encoder is sufficiently trained, represents what the intention of the user is, or what the query is all about. Basically, the semantic information that is contained in the user query, and or the meaning of the user query. And then when we get this vector representation, we put this vector representation in a so-called vector database, and here's a fine too much, where we have stored all our documents or parts of our documents as vector representations before. So a vector database is nothing other than you can imagine it to be like a traditional database where snippets of parts of our documents are saved as vectors. And how do we get to this representation? Well, we just simply pass it through the same large language model and generate vectors from that. And when we pass our vector representation of the user query into our vector database, we can, of course, perform a mathematical operation. And this mathematical operation can just be a lookup of the most similar vectors in the database. And similarity here can be defined through multiple different ways, but classically, the similarity is defined as the cosine similarity. And the cosine similarity is just a measure of how similar vectors are. So like intuitively, it's the angle between vectors. So, and this is what I try to sketch here with this representation, where the top line may represent a vector and the bottom line may represent a vector. And how similar these vectors then are can be described through an angle between the two vectors, right? So if they would be further apart, then the angle would get greater. And if they're closer, then the angle gets less. And the simple mathematical operation that happens here that now is just to calculate the angle between the query vector or the vector from the user query and all the existing vectors in the vector database. And with this operation, we can then just look for the closest vectors in our vector database. So for example, and this is usually denoted as top k. So we want to retrieve the top k closest answers to our user query. So for example, k could be 5, and then we just retrieve the top 5 closest answers to our user query. And when we have done this, we can just find the corresponding parts in our text documents and just take those parts. So we don't like take all the vectors that we have and pass them on in the next step, but we look back to what kind of text is represented with a vector that we found. So, and like, why do we do this? Why don't we stay in this nice mathematical space of vectors? Well, because we want to use this all the documents that we found or parts of the documents that we found now to pass this to our next large language model. And usually the next large language model is not trained to handle vector inputs directly, but it's trained to handle natural language input directly. And so what we are doing now is we just take the documents that correspond to our top 5 documents closest to our user query, and we just put them together. We can just string them together in a list, for example, and then all of this, and we combine this with our original query, of course, and then all of this will be fed into our next large language model. So, and this is a large language model decoder or generator, basically something that is, from an architecture perspective, extremely similar to ChatGPT or Llama or all the large language models that exist out there that can generate text for you. And then the task of this large language model is simply to match the not the closest, but the answer from our vector database or the document from our vector database that matches the query from our user the most. And then it's supposed to generate a text based on this. Or it uses the information that is contained in the user query plus the top k documents that we pass to it, and generates is supposed to generate an answer from that. And ideally, in our top k documents that we retrieved, was this information contained? So was information contained about supplier 12? Was information contained about shipment 1337? And there was also the information that James Smith is responsible, and maybe it already has access to phone number and email contact, and might be able to provide this to the user based on the information that have been retrieved by the encoder and the vector database. in the first step. Okay, so we've gone through the entire pipeline once, and I was a little bit quick, I think. So maybe it's a good time to open the space for some questions. And if you like, you can also interact with the board directly by sticking some sticky notes on it. And yeah, if you feel like there was something that is not super clear, and yeah, maybe we can just take a couple of minutes to reflect upon this, because on the surface level, I think this is maybe a little bit complex, but it might be nice to understand like the very general concept in order to follow with the steps that come next. Maybe if you don't want to engage directly, I can also like type in the chat. I understood everything. You can give a thumbs up there. And you can give me like a thumbs up or thumbs down for one of those messages in chat. All right. Okay, cool. Some of you understood everything. That's nice. Then maybe you can take over then. And you can maybe, Joachim, would you be comfortable in asking direct questions? And then I would just give this over to the audience, and particularly to the ones who said I understood everything. And then maybe we can engage in the Miro board together and yeah, go through it again. We have enough time, I think.
Is it just me who has only commenting and no editing rights in Miro?
Oh, that's not good.
Alrighty. Okay, stuff is changing, and I can add sticky notes.
Cool. Nice.
Maybe one question to tease out whether you got the core, one of the core concepts. Like, what's the benefit of vector search over classical search? Because I think the question like who is supplier 12 or who is responsible for shipment XYZ is very close to a classical SQL query.
Yeah, thanks. Good catch. Yeah, does anybody have an answer to that? You can also put down sticky notes if you're not sure, and we can just go through them and see what kind of ideas you had. Cool. So yeah, one answer is matches similar / related terms to one another. And this is the benefit of a vector database. And yes, I think so too. Maybe let's get a little bit more into that as well. What exactly does similar / related terms here mean?
So in the upcoming workshop, for example, we'll be building a chatbot for kitchen recipes. And there a classical search is, I have these ingredients. I have onions, I have potatoes, and whatever. I have chicken. And then if you would do a classical SQL query, search for all the recipes which have the ingredients onions, carrots, and chicken, or one of them, then you would not get recipes where there is a shallot or some other beetroot or like pork, as an example. And the benefit of having similar or related terms is that onions, like the embedding models, the vectors for onion and shallot are closer together than onion and milk, as an example. This is why this kind of search is so powerful, because the users of the search don't need to be aware of the full context, because they don't need to type in all the options. Give me all the recipes which have a shallot or an onion or any other kind of onion related thing. And for these use cases, it can be really useful. For other use cases, a strict lookup, I have an ID, I have an address, I have this exact term, and it can't be like changing just one digit means a completely different thing. A classical search can still be very, very useful.
Yeah, cool. Thanks a lot, Fabian. Exactly. I think this all boils down to the quote unquote black magic that happens in an encoder large language model, where these large language models somehow are able to extract or like very, very big quotation marks understand the meaning of certain words, because they have seen these words 100,000 times in many different contexts, and from these contexts they can build up like quote unquote understanding of what this word means in certain contexts. So for example, like the best example for this is always the word bank. In German it has multiple meanings, but also in English it has multiple meanings. So bank can be the money institution in English, but it can also be the border of a river, right? Or like the side of a river. And still large language models are able to quote unquote understand what bank means in certain sentences, just based on the context of the other words around it. So usually when you talk about bank as a money institution, you talk about money, you talk about deposits, you talk about maybe robbery or something like this. And when you talk about bank in the context of a river, you talk about water, rivers, flow, maybe shipping or something like this. And from this, the large language model is able to distinctly assign meaning to the word bank in different contexts. And how this looks like in a vector representation then is that the word bank gets represented very differently in terms of vector representation with different numbers or different vectors based on the surrounding context. And therefore you can make a very good distinction between the multiple different meanings of bank. Yes, and whoever added semantic understanding, yes, this is what I also mentioned before, like with semantic understanding or semantic processing. Okay, I think, I mean, there's one big sticky note, but nothing is written on it. So, do you feel like the explanations that we gave helped you a little to understand this a little bit more, or are you still somehow in the dark about how all of this works? Okay. No new sticky notes are being added. So this like the ability of neural networks to generate these vector representations of meaning is basically or it is at the core of why neural networks are so powerful. Um, and why they can be used in such a flexible way, so to speak. We have previously encountered this, I think, only once, and it was only on one slide, I think, that neural networks can do this. I think previously we just talked about like very specific quote unquote problems, like a classification problem or like a regression problem or something like this. And there we always looked at the output of the neural networks, the network in the context of the problem that we have, right? So we looked at a binary classifier with like one output neuron where we just said everything close to 0 is a dog and everything close to 1 is a cat. And like in this case, we only just have like one value that can be between 0 and 1, right? But of course, we can also have multiple values as an output of a neural network. And these outputs then don't necessarily have to correspond to categories or something like this. They can also correspond to a more abstract concept. And this is at the core of these large language model encoder networks, where the output does not necessarily correspond to anything that is tangible. It's just a vector that is being put out, but the mathematical information or the information that is contained in this vector can be easily used to transfer between the mathematical world and the real world. And maybe this will get a little bit more understandable when we talk about BERT later. And BERT will be our large language model encoder for today's session. And there it might get a little bit more intuitive how these vector representations of sentences relate to the real world. Okay, here is a new question. Does Llama and other large language models really use the embedding directly? Isn't there a separate embedding model used for this, and Llama is only responsible for generating the answer? Yes, exactly. Sorry, this might have also been lost somewhere. So we don't use the embeddings directly. So we don't use the vectors from the vector database as a vector representation directly. We just use this vector database here to look up the closest answers. And then we go back to our classical database and retrieve the written text that corresponds to the vector. Maybe let me illustrate this. I mean, I think you already got the answer, but maybe let me illustrate this for everybody else as well. So there's a direct correlation between this and this, right? I'm just going to make this black, red. So that was really bad. Sorry. I mean this. So there's a direct correlation between this text here, so the input query, and this vector representation here. And I mean, so this is just this vector representation is just this particular input query passed through our large language model encoder. And of course, we can do the other way around, right? I mean, we don't need to like pass this vector through our decoder, but we can just say, okay, so this vector here on the right side corresponds to our query, and we retain this link, right? So that's this vector here on the right side corresponds to this input query. And we can do the same thing for document encodings as well, right? So let's say we have a document here. Maybe it's suppliers 2024. It contains all the information of our suppliers that we have from 2024. And then we pass this document through the encoder, get a different vector, and we just store this vector in our vector database. But we could have, of course, then still this link between all of our suppliers and a particular vector in our vector database, right? And what we can do then, after we have found the top 5 closest vectors with our vector database query, is we can just relate all the closest vectors back to our original entries. So we can do this operation here, right? Where we
one suggestion.
Sorry.
We'll go closer or in more detail look into this process in the RAC workshop. I think where part of the confusion is coming from maybe is down here. You wrote LLM decoder and generator. But this is not the mirror model used here. It's just an LLM.
Yes. Sorry.
So
yeah.
This query plus top K document text is the actual text and not the vector. And the question whether you use the decoder or the embeddings here is correct. This part gets fed the literal human readable text and not the vectors for decoding.
Yes.
Whether Llama uses embeddings inside, I guess, is a question of term definition. How do you call the activations inside of the model? I would call them possible embeddings as well.
Yeah, I'm actually not sure if Llama uses like the transformer encoder and decoder architecture in the same model, because I think ChatGPT, for example, is just a decoder. But yeah. Okay, so sorry, I hope this didn't lead to any further confusion now. So I'm just gonna tag this here. This is natural language text. This is everything you can like everything that gets fed into the decoder is human readable. It's just the query and the top K segments of texts that have been retrieved from the vector database. So everything that
and then the most important question. Sorry.
Yeah.
How do you know the best answer?
Yeah. Yeah, maybe somebody can.
Idea?
Yeah, maybe somebody can add a sticky note. It's really good that we spend some time here because this is somehow good to know, good to understand for the rest of today's workshop. Fabian, are you satisfied with this answer?
Yes and no. So how do you know the best answer? Through training, but you still need a metric to measure the training is going in the right direction. I mean, this kind of machine learning we are talking about here is unsupervised learning. So there is no inherent best answer. It's only the meaning that gets applied afterwards by the humans. I would say for the question of, I have this text, give me these snippets which relate most closely to it, you need to create a evaluation data set where you have known snippets you want the vector search to retrieve. And then you can measure how many of these expected answers get retrieved from the vector database and either tweak your search function. So here we have top K, give me the top 5 closest sinus distance results. Or you can tweak your embedding model so that dissimilar terms become more dissimilar. But to find out what the best answer is, you need a set of question and expected answers where you then can measure and apply a metric to. And then you can train. So I agree.
Exactly. This is a really nice transition to the next slide already. And maybe also, yeah, let's just look at that slide. It's again a short poll, and maybe it's also a little bit of a controversial poll. I will just open this and give you another 1 minute. The question here is from my side. Where do you think the main quote unquote intelligence needs to be in this entire system? Of course, it needs to be at the level of the human, of course. But if we only look at it from a technical perspective, where do you think the heavy lifting needs to occur? And I will just open this vote. You have 1 minute. Two people still can vote. I hope this doesn't count the two of us, Fabian.
I declined.
Okay, nice. Okay, let's see the results. Okay, so 6 people say the heavy lifting needs to occur in the encoder. 2 say it needs to occur in the vector database, and 4 say it needs to occur in the generator. So, I mean, Fabian has already alluded to this. You can have multiple points where you tweak your the performance of your RAG system. And I mean, like when I created this, I thought that the correct answer here would be that the heavy lifting needs to occur in the encoder because it needs to meaningful distinguish between different topics and different queries and things like that. But of course, the answer is not as straightforward because also your decoder or generator needs to learn what kind of things it needs to look out for given a certain query. And therefore, there are multiple different points where you could tweak your retrieval augmented generation system performance. But yeah, I mean, for the sake of the rest of today's workshop, let's just act like this is the right answer, even though it's not straightforward, because this serves then as a good motivation of why we want to, yeah, train a new encoder or build our own encoder based on an existing neural network that we then modify a little bit. Okay, this leads me over to our last slide in the introduction section, which is the motivation of today. And this motivation is that we start off our system. So first off, we will not build a rack system. We will not build it like a generator. But in the context of the rack system, it's good to know that the encoder does some part of the quote-unquote intelligent part of the system by encoding different queries or different inputs in a dissimilar way, so that then in a future application you can just search for the closest ones, and you have a reason, or you can reasonably expect that it will return you documents or text snippets that are somehow related to the input that you put in. And today we want to train an encoder or modify an existing encoder so that it does not, or where it starts off as being a more or less universal modeling encoder, where it has the capabilities of modeling many different topics in a different way. So for example, topics from literature, history, maybe places, persons, maybe some other topics, and they are very meaningfully distinct. This is a good place to start, of course, but we want to make the domain more narrow. What does this mean? So we want the encoder not to be able to distinguish between these very many different general topics, but we want to make it an expert, so to speak, on all the topics from natural sciences, where it's able to distinguish between very niche questions from the natural sciences, from many different domains. So for example, here it's like a chemistry question or a chemistry topic, or maybe like a type of beetle or something like this. And it's supposed to give us good distinctions between chemistry and biology, of course, but also within biology, a good distinction between one kind of beetle and another kind of beetle. So we make it from a general system into a more specialized system that then retains a good performance within a specialized domain. In the context of retrieval augmented generation, if you're planning on building a chatbot, maybe you don't want to have your chatbot be responsible for everything, and then the performance is lacking in all domains somehow. But you want your retrieval augmented generation system that is very specific for a domain in your company where you have many different types of information that are not easily distinguishable by someone who is not trained in this domain. For example, like if you, I don't know, if you are, I don't know, the not constructor, but if you're making fertilizer, for example, maybe you're making many different types of fertilizer with many different chemical properties or biological properties or something like this. And you want to have a retrieval augmented generation system within this domain of different fertilizers. And there's lots of information about these fertilizers, where they differ and where they are similar. Maybe you want to then train your encoder specifically in this domain of fertilizer information in order to be able to build a rack system that has the ability to answer questions or answer queries from users within the domain of very technical knowledge, or like very the chemistry and biology and other properties of fertilizer. And for this it makes sense to then train an existing encoder that can already process natural language, but to train it on your narrow domain, for example, in this case, we focus on natural sciences. Okay. Maybe a question to you, an ad hoc question. What could be the advantage of doing something like this? I mean, I've already talked about it a little bit, but maybe we can collect a couple of answers. Um, Maybe if you think about your own domain within your company, maybe you can share something. Uh, I can, for example, think of something where maybe we can collect some other advantages of doing this. And of course, if you have questions, you can also put them on sticky notes, and we can engage with them. Some other suggestions from you? Okay. Have I completely confused you? Or maybe it's not quite clear what an encoder actually does still, or is.
I guess it might become more clearer the closer we get to working with it.
Yeah, makes sense.
So, like, I can explain the response I gave. This was an actual use case we had a while ago, where we wanted to build a chatbot for legal documents, and there are many pre-trained embedding models out in the world, as Johannes described in the upper part here. They are trained on very well on the whole language, on the whole domain. And then when we looked at the vector distances between different legal texts, the embedding model basically said there is no difference. The encoder said there is no difference. Similar to me as a human who doesn't understand legalese, who is not a lawyer, to me all legal text looks pretty much the same and pretty boring. And maybe I understand some keywords about healthcare and other keywords are about, I don't know, security. However, this made it difficult to do a good vector search in there, because there's also a lot of boilerplate code. So a lot of, not code, but sentences, a lot of repetitions in the words being used and in the formulations being used. And for a generic embedding model, this makes these two texts look very similar because they start in the same manner. So all European laws have the first 3-4 pages similar, which for the embedding model, the general embedding model, makes these texts very similar to each other. And then we realized, okay, this is a problem. We didn't have enough time in that short project, but ideally you'd be fine-tuning the embedding model just on these legal documents, and then make the model aware that certain similarities don't mean anything, just because it's always the front matter of a law. So increasing the distance, the vector distance between the different database entries could be one goal of fine-tuning your encoding model.
Yes, thanks a lot. I also feel like this is something where you as small and medium-sized companies also have an advantage. Some of you are very specialized in their fields and have a lot of documents that are very particular to the business model of your company, but also the domain that you are in, the economic domain where you're in. And there, when you try to build such a chatbot, you might be able to leverage the knowledge that is in your company to build something that is very unique and that couldn't be built from other people or like from other companies, just because you have so much domain knowledge. And there it makes sense to if you build a RAG system, to fine-tune the encoder on the documents that you have in order to make it knowledgeable in the domain that you are operating in. Cool. I originally intended this slide to be like the great revelation of motivation why we want to do this, but I'm not sure if everybody is so excited as I am about building your own encoders and making your systems more performant in that domain. But for today's exercise or today's toy use case, so to speak, we start out with a universal or more or less universal encoder, and we transfer it into the domain where it's able to understand differences between natural science domains or documents from natural sciences. And this is our goal, basically. And whenever we talk about something more technical, because we will dive a little bit more deeply into the technical aspects of this, we can go back to this slide and whenever we ask ourselves why are we doing this, then we can go back to this slide, and this is supposed to act as our motivation for today. Cool. This would be it for the first chapter. This is the introduction chapter, and we would now go over to chapter 2, which is a deep dive into large language models, or like how BERT works, what we do, how we train it, and how we continue with this. And then in chapter 3 is more about an evaluation of the system and a discussion about what the advantages and disadvantages are. And yes, I would start with chapter 2, and in half an hour, maybe we can take our first coffee break. Let's see how far we go. And again, feel free whenever you have questions or whenever you feel like something wasn't that nicely explained, then just feel free to write in the chat or add a sticky note to the right or left side of the slide, and then I can see it. Cool. Then we will just start with chapter 2 here on the top, in the middle, with BERT. So what is BERT? BERT is an encoder. And what does BERT stand for? It stands for bidirectional encoder representations from transformers. It's a nice technical term. Maybe you have also already encountered this term transformer whenever you looked up what ChatGPT actually stands for. ChatGPT stands for generative pre-trained transformer. So BERT and ChatGPT have the same lineage, or they come from the same idea, basically. But a little bit more to BERT. So BERT is the quote-unquote grandfather of large language models. Why is it the grandfather? Because when the paper came out that outlined this transformer architecture, this is the foundational architecture that all large language models use today. And it's actually also being used in other applications. But this is what basically gave us the ChatGPT breakthrough in 2022. And BERT came directly after the paper was released to the public, which outlined the transformer architecture. I think the transformer architecture was outlined or was released or published in 2017, and BERT then was published a couple of months later. So it also comes from Google. So Google, or researchers at Google built the transformer architecture, and they then built BERT based on the transformer architecture. And therefore, it's already quite old. So it predates ChatGPT by 4 years. But it's still somehow usable as an encoder, or as a starting point for a good encoder. It's publicly available. You can go on Hugging Face. We will talk about more about Hugging Face as a web platform where you can download models in the RAG workshop, or Handling of Pre-trained Models workshop. And it's still stored on Hugging Face, and you can still download the model for free and use it for your own use cases or your own projects. One key technology, or one key idea that is being used in these transformer networks. So again, transformer networks are like ChatGPT, so everything that we call a large language model, but also BERT in this case, it's also a large language model. It's very, very small for large language models from nowadays perspective, but back then it was quite big. Is that all of these large language models use a so-called self-attention mechanism. And how this works, we'll look at in the next slide. But this is a key idea that is being used in these transformer architectures, or everything that relies on a transformer. And BERT, as a model, is trained on a large book corpus and Wikipedia articles, and it is available in many different versions. So there's a large version that is just a bigger model. It's available in the small version, or a basic version. It's available in English, and it's available in a multilingual version. So you can, and there's also already there's a BERT network that is specifically trained on German. So you can have many different variations of the BERT network that are all available for the public. So it's a nice ecosystem to start with if you want to get into working with artificial neural networks or large language models, and you want to understand more how they work or how they perform. It's a nice starting point for that. And also, it's sufficiently small to train in a more or less reasonable time. So it's also something to consider. So how do you actually train BERT? So when the original BERT was released, there were two different mechanisms that they used in order to train it. The first mechanism was to simply give the network a sentence and then present the network with two candidates for a follow-up sentence. So for example, one example sentence for this is Albert Einstein was a German-born theoretical physicist. And then the next follow-up sentence could be either he is known for discovering the relativity theory, or a candidate could be it was founded in 1882. And then the model is tasked to decide which of the two answers is the follow-up answer. This training strategy is used to let the model learn about so-called long-distance dependencies. Here, it's supposed to derive meaning from the first sentence and then basically understand what the next sentence is all about, and then use this to decide which of the two sentences is the correct one. So this is being used on the one hand. And the other training strategy that is being used for training BERT is to simply give it a sentence and to mask out a word in this sentence or a token in this sentence. So for example, here we have the sentence, Paris is the blank of France. And then the model is supposed to give you an answer to what word is missing. You may know this from, I don't know, like preschool, not preschool, but like early years in school where you had these Lückentexte or texts with missing words in them, and you're supposed to fill in the correct words. And this is basically what the model is learning from. And there you punish the network if it gives Paris is the Hilton of France, and you reward it if it chooses the right word. So this is basically it. So this is a very straightforward way of training this model. But you can maybe already see that this training is more directed towards making the model understand how to process natural language, how to extract meaning from sentences, and how to learn certain facts about the world. But it's not so much about learning to distinguish between different topics. This comes, so to speak, more naturally because for the network, it's very advantageous to represent facts about Albert Einstein in a different vector domain than facts about Paris or some landscape or something like this. But it's not something that the network is explicitly trained on to do. And so maybe we can augment this while we do the training to make BERT a more natural science focused encoder rather than a universal network. Okay, this is just a very soft introduction to BERT. Do you have any questions to what BERT is and how it was trained? All right. Cool. Yeah, I mean, if still questions come up, just feel free to add a sticky note or write something in the chat. Then let's take a look at how BERT actually works. And I promise you, there are two very technical slides today, and this is one of them. So we can just take a couple of minutes to look at this. But if you don't understand it right away, or if you don't understand it with my explanations, don't worry. You don't need to know this in order to build a large language model by yourself, but it's like the theoretical background of how they work. And I wanted to include this in order to yeah, give you some understanding on the way in order to make it easier for you to understand more of the theoretical aspects of neural networks, or especially large language models. So so how does all of this work? So we have already learned about different kinds of network architecture, right? We have looked at convolutional neural networks, for example, as the de facto standard for image processing. And we've also looked at long short-term memory networks, right? Like recurrent neural networks where they feed into themselves again. But fortunately, all of these large language models are not very complex in this regard. They are just very large, and they basically only use some mathematical operations, and they use fully connected layers or dense layers. So all the the very bog standard layer that you can use in artificial neural networks, they use that. They don't use any fancy special layers for anything. So how does a BERT network then work? So a BERT network, and maybe we can start from the very zoomed out level, and then we can zoom in more and more and more. And actually, this slide starts at a very zoomed in stage already. So let's extend this. And a BERT network just contains sorry, I can't write and talk. It is simply the so-called transformer encoder block. And then, oops, what you do is you just stack them. You have multiple of these blocks. And you can stack arbitrary many. In the case of like BERT small, it's 12, I think. And in the case of BERT large, it's 24. And you just stack them together. And like this is like this is very simple and very stupid. I don't know. Where you just stack these blocks on top of each other, and they do all the processing. And eventually, you reach a size or like a sufficient network size to be able to process language with it. But of course, this is not the entire history because or story, because of course we don't know what an encoder block is now, right? So an encoder block in this illustration on the right side is just this part of the transformer architecture. Maybe I can do some nice illustration. Like this. And then I will just overlay like a filter so that we don't care about this right side. All right. So all of this that is not that is not highlighted, this is the decoder block. There are two different kinds of blocks in the transformer architecture. There's the encoder block and the decoder block. And as the name BERT already suggested, remember there's the encoder in the name. it just uses this right side, or this left side, the encoder block, and it does not use the decoder block. The decoder block is something that you use if you use, or if you build a large language model that is supposed to generate text as an output. Okay, so now we can see this encoder block, and let's go through this encoder block once and try to understand what's going on. So we start here at the bottom and we end at the top. And we start with some inputs. So in the case of this illustration, these inputs are actually a raw text. So this could be some fact about Albert Einstein, for example, and this would be an input that we put into the encoder block. Then this input is being transferred into input embeddings. What are input embeddings? Well, basically, we have to translate the raw text into a numerical representation, right? And for this, we use a so-called tokenizer. The tokenizer splits our text into this numerical representation, and it does some more work. It splits some words in order to make the representation more efficient. But we do not care about this so much because it's not so super important. The only thing that you need to know is that the tokenizer changes an input text from a raw text into a numerical representation that the network then can work with, because the network can't of course work with literal letters. So we get these input embeddings, or input and a tokenized representation. So I would just write 1, 2, 3, 0, 1, 2, 3. This is how our text looks like at this stage. Then we get a positional encoding. We don't care about this that much in this explanation here, because it's not super relevant for understanding how the encoder block works in itself. The positional encoding just makes sure that the order of letters is being retained, right? Because if we would scramble up the order of letters, so if we would say, I don't know, like scramble the letters between in Albert Einstein, then the meaning would get lost. And this positional encoding makes sure that the letters basically stay at the same position. And therefore, we are doing this encoding here. We basically like add some information to it. But other than that, it's not important to know what's going on here. It's some mathematical stuff that's going on. Okay, so then this the text, or the text in numerical form, gets passed into a so-called multi-head attention block, and we leave this as a black box and look at it in the next step. This multi-head attention block then delivers an output. This output gets added and normalized with the raw input here. Let me add a label for that. And this is a so-called skip connection that is being used here, where the raw input, or the unprocessed input, and the input or the input that has been processed by the multi-head attention block get added together. Another question is, why should we ever integrate non-processed input with input that has been processed? Why should we do this? Like, why do we basically add something that has been not processed to something that has been processed, while we of course want the network to process something, right? And this is because we do this because sometimes the especially when dealing with highly parallelized networks, maybe this multi-head attention block, let me color code this in red, this one. Maybe this multi-head attention block in itself is already overfitting on our data. And remember, like this is one encoder block, so maybe the input here is not only like the raw text, but it's already something that has been processed before, right? So maybe this multi-head attention block here is overfitting or does not meaningfully contribute to diminish our error within our network. And in this case, we basically want to skip this. We want to skip this multi-head attention block because it's just introducing more error into our network. And therefore, if we want to skip this, we need to skip this processing step entirely and be able to, basically still have access to our original input that came in from the very beginning, or like from the very beginning of our pipeline, of our processing pipeline. And therefore, we do the skip connection here, so that whenever a multi-head attention block is overfitting, we can just discard it basically and throw it out of the pipeline. And this is basically also what the feed-forward network here is then for. Feed-forward is just another name for dense layer or fully connected network, fully connected layer, which is supposed to filter out everything that comes from a potentially overfitting multi-head attention block here. And of course, like if you just add the original input and the multi-head attention output together, then this is a mixed signal, and it cannot it needs to there needs to be some further filtering operation in order to separate the desired output from the non-desired output. And depending on whether or not our multi-head attention block is overfitting, the desired output is either the raw input or it's the processed input from the multi-head attention block, if the multi-head attention block is not overfitting. And therefore, we have this feed-forward network here. Again, we add a skip connection. This is relevant for when the feed-forward network is not able to separate the two signals meaningfully from one another. They get also added and normalized. The normalization is just to keep the whenever I don't know if you've already worked with like convolutional neural networks, for example. You always have to make sure that the input to a new neural network layer has the same dimensions, and therefore we do this normalization step here, and at these two locations here. And then this is basically the output of our encoder block. So everything that happens within the encoder block is just things that happen within our black box, the multi-head attention layer here, and then just some skip connections and a simple filtering operation here, which filters the output from our normalization operation here. Let's delete this. Okay. So this is in an encoder block. And of course, the magic happens here within this multi-head attention block or segment within the encoder block, of course. And now maybe let's zoom into the multi-head attention. You give me feedback if I'm too fast or if I'm completely losing you. Or you add some sticky notes. Okay. So what is the multi-head attention block? The multi-head attention block is a cascade of processing or it's a multiplication. Not multiplication. It's let me get the thing. Okay, so yeah, first of all, let's look at it. We have a multi-head attention block consists of many different scaled dot product attention blocks that are working in parallel. So what does this mean? Working in parallel? Maybe we can go to the bottom here. This just means that we just have multiple of these scaled dot product attention blocks, and they run in parallel. And then we get our input, and we put the input into just many copies of this architecture. Then this does something internally, and then in the end, and this is here illustrated here on the top with concat and linear. All of the output of this gets aggregated again, or just put together like in a list. And then this gets fed through another linear layer. So this is the idea behind this multi-head attention block, where you just do massive parallelization within these scaled dot product attention blocks. And you aggregate the output of this and then push it forward. And now, of course, the question is, what happens within the scaled dot product attention? But also maybe like, what is V, K, and Q here? Why does this have these weird names? And this is because, or what this means, and this is it comes from the original transformer paper as well. V stands for value. K stands for key. And Q stands for query. I mean, these terms in themselves don't mean anything now, of course, because we don't know the context. And I mean, like these letters have been retained from when the authors of the transformer architecture first started thinking about this. They thought about the transformer layer, or the scaled dot product attention block, to be something like a lookup operation, where you get a query, a request, and this query gets translated into a key, or gets translated into a key lookup and the value lookup. Or the value is basically what you retrieve, right? And the key is like the query translated into some operation. They kept the name and they kept this intuition, but in the context of multi-head attention, this doesn't really make a difference. You could also call it differently, because there's not a meaningful different operation going on between all of I mean, there is some difference in how these how V, K, and Q get processed, but they don't necessarily correspond to like a lookup operation. They correspond to some black magic that's going on in large language models. Okay, so this is the multi-head attention block. Again, it's just linear layers here. This is again like fully connected layers. Then they get fed into a scaled dot product attention operation. Then they get put together again. And then there's another layer, a linear layer, that computes like what kind of aspect of the concatenation gets filtered through more or less. So lastly, then is the question, what is the scaled dot product attention? And this boils down to a very basic mathematical operation, which is here in this last block here on the right side then, this matrix multiplication. And this matrix multiplication is just the computation of the dot product of two vectors. And also called matrix multiplication. So the query and the key get multiplied with one another. Then they get scaled. Then they get put into a softmax through a softmax function, like a activation function. And then they again get matrix multiplied with the value here. So why do we do this? So on a very intuitive level, what all of this operation here does is that it tries to find a relationship between values or the content of Q and the content of K. And how this relationship is expressed is that it's so it basically like tries to find a connection between the values of Q. Let's say this is Q and this is K. And through this matrix multiplication, we can infer how a certain entry in our matrix is related to an entry of the other matrix. And if we go maybe like a couple of steps back, what does this mean in plain English? This means because these matrices or vectors still represent some kind of language. Let me give you an example. Let's say we have this is our input sentence, right? That came in many steps before. And what this dot product or this matrix multiplication here does is, and again, like Q and K and V represent the same input, right? So Q is this sentence, K is the sentence, and V is also the sentence. They are all the same sentence, or the representation of this sentence. And what this here does, this matrix multiplication, is it multiplies single words within the sentence with one another based on the results of these linear layers here. And what these linear layers do is they scale up or scale down these values that represent the words of the sentence. And what the scaling then does is when the scaling gets high forward in the key, for example, then the impact of, or let's say the first one here gets very high. Then it says the word Albert is very important for, and then it gets multiplied with all the different words here in the query, right? And this, so in this case, Albert is not very important for Einstein. Okay, yeah, sorry. Let's not look at the particular numbers here, but let's just like think about this from a language perspective. It says Albert has a certain relevance for Einstein. Albert has a certain relevance for German. Albert has a certain relevance for Born. Albert has a certain relevance for physicists. And all these connections here represent these numbers here. And if you think about it, then you can basically build a connection between all these different words, like a connection like this. Maybe let's say we say like red is very important. Einstein and physicists are very closely related. And Albert and German are very closely related because Albert is the typical German name. I don't know. And then here maybe like born is related to is born. From a grammatical perspective, maybe is and born are related to one another. And maybe and German is very closely related because the is the grammatically, I don't know what the term for this is, but a German has more importance than German. And again, like physicist might be related to some other word. Maybe physicist is related to German because German physicists are, or it's important to know the relationship between German and physicist. And this is all what this matrix multiplication here does. In a mathematical way, but this is what it basically boils down to find the importance of one word in the sequence to another word in the sequence. And this is what happens here in this first matrix multiplication step. Then the result of this gets scaled again because you need to keep the same dimensionality. It gets fed through a softmax function to squish it down in a certain value range. And then this matrix multiplication happens again. And on the second time that it happens, we still have the same sentence, but now basically the same sentence gets multiplied with not itself, but it gets multiplied with all these differently colored connections that I did here. And these differently colored connections are representing the importance of one word to itself or to another word, right? So basically what we get then here is like on a conceptual level, we can maybe have something like this, right? Where Albert Einstein maybe is very important and physicist is also important. Oops, oh, sorry. I can't handle my row. But maybe German born is not that important anymore. And so basically the output then of the scaled dot product attention is basically like a filtering operation of importance of certain words within the sentence. And what is like how do we now determine what is important and what is not important? Well, this is dependent on our training objective, right? What the network then learns from this is is basically that to represent certain semantic connections between very particular words. For example, this connection between Albert Einstein and physicist is what the network then learns, because maybe it's important for the network to know that Albert Einstein is a physicist, right? and this is the magic basically that happens within the transformer architecture, that these relationships here between these tokens or between these words can get extracted through this very, very simple operation that happens here. And you parallelize this to be able to extract more and more information from this sentence. Because I mean, in the example that we looked at, we only looked at this like semantic relationship between Albert Einstein being a physicist, but maybe in other tasks, a grammatical or the grammatical information that is inside a sentence is also important. So, for example, because this sentence contains a German, this is different from the German, for example. We could think of an example where the German is used exchangeably with like a certain person, maybe in a story or something like this, where there is the German who's being referred to, and then the network needs to understand that the German is a reference to a character or to someone who was mentioned in the previous sentence. And this parallelization enables the network to extract all of these relevant information in parallel, and stacking all of these encoder blocks on top of each other makes it possible for the network to extract the relevant information at different points, so to speak. So maybe a very early encoder block is then used to look at grammatic regularities, whereas a later encoder block is then more specialized to distinguish between like Albert Einstein in particular and German physicists in general, or maybe some like time periods or something like this. All right. So this is the deep dive into how large language models work, or how BERT works, how encoder networks work. I'm sure I've lost many of you. If you're super interested in how all of these things work on a mathematical level, or more deep dives, there are many different articles and YouTube videos out there that you can look at. And maybe at the end of the workshop, I can share one with you. There's a YouTube channel called 3 Blue 1 Brown. He's a mathematician, and he has either an entire series or just one very long video on how transformers work internally with like nice visualizations and animations. Okay.
Coffee.
Coffee, yeah, that was a lot.
Do you hear the call?
Yeah, let's go for coffee. That's good. Yeah, thanks a lot. Maybe in the coffee break, yeah, you can reflect upon my TED Talk, and we can come back refreshed and maybe go into a conversation about this. Yeah, if you're interested. All right, I would say let's meet again at 11, and yeah, see you then. All right, welcome back. I hope everybody is somehow refreshed. I shared the link to the YouTube video from 3 Blue 1 Brown here on the Miro-bot. I can also share it in the chat again. I am sure that I lost most of you. Why is it the Miro link? No. Okay, I can share it again. Yeah. Okay, here you go. If you want to take a look at it. So, I mean, why is this relevant for today's topic? I mean, it's only relevant because we're using BERT and it's an encoder. It's based on the transformer architecture. So, diving this deep is not super necessary to understand the rest of today's workshop. However, it's a good background in order to know what is actually going on inside these encoder networks. Artificial neural networks in themselves have this property that they are black boxes, right? You don't understand what's going on inside of them necessarily that much. But alleviating this by understanding what the architecture is all about and what the intention behind the architecture is may help us to understand some behavior of a network and why or how we should engage with the network when using it for a certain use case. Also, I found it interesting. I don't know. And I wanted to share this with you just to have like one deep dive going on in today's workshop. However, if I still had your or if you still could follow me on the previous slide with just BERT and I lost you completely with this BERT under the hood thing, then now is the chance to get on board again and you will not have missed that much that is relevant for understanding the rest of today's session. So yeah, I hope the coffee also helps with that. All right, coming back to what we want to do with BERT. So we have looked at BERT, what it is. It's this transformer encoder network, right? And we now want to change BERT from being a network that has been trained on a wide variety of topics to a network that is very proficient in the STEM field. And this slide is just a reminder for this. And here we can have a first look at our dataset. And I collected this dataset. I don't know if I have it from Kaggle or some other place. Maybe I've pre-processed or like downloaded it from Wikipedia dumps. I'm not entirely certain anymore. I have the raw dataset lying around definitely. So if you want to have it, you can write me an email or something. But you can also find it on the internet. So this is how our dataset looks like. It's a collection of many different Wikipedia articles, and actually every entry in our dataset is not the entire text of a Wikipedia article. It's actually the text of a paragraph of a Wikipedia article. Why do we use paragraphs? Well, these large language models have a so-called context length. It's basically the maximum input length of the sequence that you can put into such networks. The large language models that you can use today, like ChatGPT or Llama 3.2, usually have a very high context length that you can put in up to 200,000, 250,000 tokens or something like this. But BERT is a small model, so BERT only has a maximum length of 512 tokens. You can roughly say one token represents half of a word or something like this. So roughly 256, 200 words that you can put into BERT at once. And so dealing with a paragraph is more easy than dealing with an entire Wikipedia article. This will probably also be something that you will be running into if you build your own RAG system. Usually you don't encode an entire document into your vector database. You encode so-called chunks, and these chunks are then just segments of your document that you put into your vector database separately from one another. Just because the encoder networks are just not large enough to handle this large amount of text. And maybe you also want to have a higher granularity of retrieval. For example, if you are if you try to encode the entire BGB, Bundesgesetzbuch, law book, then you maybe don't want to encode the entire law book in one vector, but you want to encode different paragraphs of the law book in separate vectors, so you can reference them more accurately. All right, so and this is how our dataset looks like. And with this dataset, we want to turn BERT into, I call it STEM BERT, or just a BERT network that is trained on STEM topics, natural sciences. And now the question becomes, how can we achieve this? How should we train a network like this? And okay, so this is let's skip this one, and maybe let's go into the collaborative brainstorming right away, and ask the question: how could we train the existing BERT model to become a specialized encoder for natural sciences? And for this, I've collected some sticky notes here, and maybe we can take let's say 5 minutes to brainstorm a couple of ideas from you. Okay, are the instructions clear?
Does anyone have any questions? Asking the other way around.
Good question. All right, this doesn't seem to be the case. Then I would set the timer to 5 minutes, and you can start brainstorming. We could do that.
AI inception would be if you go to ChatGPT, ask it that question, then condense the answer back into the sticky note.
Nice. Have you tried it? What does ChatGPT say?
I have not yet tried it, but
very convenient that you can just copy the question from the slide.
Make it multimodal, take a screenshot, hope that the visual part of the general AI detects the text correctly.
I think somebody showed that Claude can do this, and that Claude can also create like flowcharts and things like that.
Dirk, you now need to tell it to condense it to a single sticky note.
There's also an AI for that on Miro.
We are already living the multi-agent lifestyle.
Yes.
Putting AIs everywhere.
Awesome. Not very surprising that ChatGPT gives a similar answer twice. Cool, thanks a lot. Also, thanks to Vitis for the autocomplete science articles suggestion. And like going through the answers also from ChatGPT, there's the consensus that this could be a training strategy, right? So the autocomplete science articles, right? Where it says here in the first answer here, the first ChatGPT answer, this one, the green one, it says start with Cybert. Well, we are not starting with Cybert. Use a domain-specific data set. We already have one of those. And do masked token prediction and next sentence prediction. This is the pre-training that we are supposed to do. And for us to achieve the universal encoding, we are supposed to train the network on a semantic similarity task. EA NLI task. I'm not sure what NLI is here. Maybe ChatGPT can elaborate on this. And then it just gives us a recipe for what we are supposed to do, like tokenize the data and set up training arguments and things like that. And the other answer from ChatGPT 01 is basically also like do the same things. So gather some specific science corpus, do some pre-training on BERT, and then use contrastive learning, CSE, I also don't know what this is, to align sentence level embeddings for universal encoding. And then it says we should evaluate on domain specific tasks such as classification and retrieval and iterate on that. There's another. NLI is natural language inference. Cool. Okay, nice. Yeah, where the model is given a certain premise and it's supposed to predict 3 relationships from the statement. For example, a dog is running in the park, and the hypothesis is an animal is running outdoors. Yeah, it's supposed to generate the hypothesis and say what the hypothesis, in what kind of category the hypothesis is. So it's an entailment. The dog is running in the park means an animal is running outdoors. Yeah, cool, interesting. Maybe also a nice approach or interesting approach to do that. You might be a little bit disappointed to learn that for today's workshop, I didn't really focus on pre-training that much. Or maybe like a question to the audience, what is pre-training in this context? I can just put down a sticky note and you can write on it, what is pre-training? You can also unmute yourself if you feel like you can just answer this in a sentence or two. It's also quite a trivial question, I think. Oops, sorry, I was muted. Yeah, next token prediction is an answer. I would say this is more like the strategy, but my question is more in the domain of what kind of role does pre-training play, or what does it mean to pre-train something? You can infer this from what ChatGPT gave us as a strategy with the first part, where it says do next token prediction and next sentence prediction in combination with a new data set. What does this entail, or what does this mean? Maybe Fabian, do you want to give your intuition to this?
You're way deeper than my poor MLabs brain usually goes. So my intuition is that tools or strategies like next token prediction don't get you to the final well-working embedder, but help set all the network weights and biases already in an easy manner, so that when you start with the full task, you're much more likely to start with values inside the neurons that get you to a well-working embedding model, because you started with the simpler task of predicting next token.
Exactly. So you basically like you sensitize the model towards the natural science domain without explicitly training it as an encoder. You just maybe during the original training, there are some terms or some relationships that it hasn't seen before that we can cover with our specifically in the natural sciences originating data set. And then it can adjust its weights in order to process text from natural sciences more. Maybe if you've ever read an academic paper, usually academic papers have a certain jargon. And they differ quite a lot between, for example, social sciences and computer sciences, where there's a certain way of expressing yourself within this scientific domain that is more accepted or that has certain meaning. And if we pre-train our BERT network with the same training strategy that it was originally trained with, then we can sensitize it towards this jargon or this way of expressing yourself. And this would be pre-training, where we don't necessarily train our neural network already on the task that we wanted to perform later on, but we want to give it like foundational knowledge. In the context of computer vision, for example, here it would be that we for example, pre-train a vision model on many different classes, many different objects in the world to distinguish between. So cars and animals and vegetables, for example. And then later we want to fine-tune it to be able to distinguish between different kinds of birds, for example. Then it has already learned how to process images in general, and maybe also learned how to make a difference between like natural objects and human-made objects or something like this. And then it's easier for the model to then fulfill the later task, because there maybe it has already learned how to distinguish a bird from trees or some background images, and then it only needs to learn certain features of different birds, such as like I don't know, beak color or the shape of the wings or something like this. So this is where you use pre-training, and in our context, and this is also what ChatGPT suggests, is to pre-train our model on a science data set, basically. And for this, we can use next token prediction. And there is one answer, I think, and this was directly related to the answer of 01, where it suggested to do this simple contrastive sentence embeddings technique. And this is then the task that we want to train our model on in earnest or outside of free training. This is actually what we want to do. And here, this explanation from 01 is simply, or it says that we train the model to produce these high qualitative sentence embeddings by using a contrastive learning objective. So what does a contrastive learning objective in this context mean? And this means that the model is encouraged, in the words of 01, to distinguish between semantically different sentences, and to map these embeddings into different regions in the vector space. So, I can just reveal the next card here and just immediately make this connection here to one of our slides in the previous session that we had, where we looked at a typical network architecture. And here we said, okay, well, embeddings are just values at a certain layer. So when you put something in, you get the values of the neurons and at a certain layer out, and you can do something with it. But you can also use an encoder network, for example, to not generate necessarily like a objective-oriented output. For example, here saying output 1 corresponds to cats, output n corresponds to dogs or something like this. But we can also just train the model to produce these embeddings or encodings. Right? I will use this term interchangeably, embeddings and encodings. And so just this as a reference to that we have already seen this term before in the last session. And this is what O1 here means, that we should train the network on a task where it produces embeddings that are that occupy a certain space in our vector space. You can think of a vector space just like a usual 3D space, right? Where let's say you are in an empty room and you train the network to place or everything that is in the domain of physics into the in front of the door or something like this. And everything related to biology, it's supposed to place next to the window because biology is related to plants or something like this, right? And you can think of vector spaces in the same domain, that they have a certain they have certain properties or certain directions, so to speak. And we train our model to naturally make it occupy certain regions for certain topics. And so it basically like forms these high-dimensional clusters within its embeddings or encodings. So this is what ChatGPT suggests that we should do. And where basically, and I think ChatGPT puts it very well here, the objective of this simple contrastive sentence embeddings technique is to basically encourage the model to find these similarities between certain topics and represent these similarities within its output. And this is actually what we want to do. We will not be using this simple contrastive sentence embeddings here, also because I feel like this is not like an explicit strategy, but more like a general strategy to do it. But we will be using this triplet learning approach here. And basically, this triplet learning approach that we will be using is a way to achieve this simple contrastive sentence embeddings goal. So our goal here is, again, our goal that we want to achieve with this triplet learning is to build a model that can represent similar inputs similarly in its output embeddings. Meaning whenever we feed like an article about a beetle inside the network, then it should give us a vector output that is mathematically very similar to another beetle or to a related topic. And so the question now becomes, how can we do this? And the strategy that we will be using is, again, this so-called triplet learning. And this triplet learning relies on these three terms here. The terms are anchor, positive, and negative. And what we can now do is, I'm just going to copy the description of our dataset up here, down, and illustrate this. We can say, okay, so we know that here in this dataset, everything, every paragraph that comes from the Wikipedia article Google Translate is somehow related to one another, right? Because one paragraph in the Google Translate article covers a certain aspect of Google Translate as a topic, right? And so we already have a relationship within all of these paragraphs. So for example, we have the first paragraph, we have the second paragraph, we have the third one, and they all share the relationship that they are all part of the Google Translate article, right? And now what we can do is we can say, okay, so we want these paragraphs to be very close together, right? In the embedding or in the embedding space that the model is to create for us, because they cover a similar topic. most likely. And so when we build our data set now, we choose one paragraph from an article as the so-called anchor. This will be our reference point, basically. Our vector reference point, a point in space. Then we select another paragraph as our positive. This is an example where we say, okay, so this positive should be very close to the anchor point. This should be minimized, the distance here. And then we can just pick an arbitrary different paragraph from another article that is not from Google Translate, but it's maybe from some topic in biology or something like this. Right? It could be a paragraph about the wing shape of a beetle or something like this, right? And we pick this as a negative, and the relationship between the negative and the anchor should be maximized, right? And this is triplet learning. It's also using the Siamese network architecture. How we can do this is we basically feed all the paragraphs into the network at the same time. We don't stitch them together, but we build a network architecture that accepts the anchor, the positive, and the negative as inputs. Then we pass all of them through the network, and we generate these embeddings here. And I've just represented this as vectors again, right? Here, the red line represents the anchor vector. The positive is represented by the purple line here, and the negative is the yellow one. And then we can do a simple distance calculation between the vectors. For example, we could do again like calculate the angle with a cosine similarity function, for example. And then we can compare these two distances with one another. Like we can compute the distance between these and the distance between these two vectors. And when this distance here, the distance between the anchor and the positive is lower than the distance between the anchor and the negative, the network gets a very small punishment, or it gets a high reward. And if the distance between the anchor and the negative is actually smaller than the anchor and the positive, then the network gets punished, or it gets a low reward for that. So that's the intuition behind triplet learning. Maybe we would just like leave it here, and I can ask you if you feel like that you understand the intuition behind it, or maybe where you are lost, if you can identify a point.
Nothing to it but to do it.
Hmm? Okay. I mean, for me, of course, this is obvious. But maybe, Fabian, can you come up with a question that we can ask the audience to solidify their understanding?
Thinking of questions. harder than thinking of answers.
Yeah, true. Okay, yeah, maybe I have a question then. Yeah, and that's good because it relates to triplet learning as a concept. My question to you, audience, would be, what criteria need to be fulfilled towards our data set? What criteria need to be fulfilled in terms of no, it's okay. Let me first finish this and then we can reformulate it.
Maybe I'll reformulate it. I think I know where you're going. So we looked at a data set where there are paragraphs from Wikipedia articles. What would be a bad data set where this kind of learning doesn't work?
You can also gladly stay in the text domain if you want. There's one suggestion, the data set containing similar topics. Does anybody else have an idea?
I mean, if they are similar but not the same, then you just get a specialized embedding model, right?
If you want to discuss this out, I think this comes from you, right? Maybe you can share your thoughts.
The example I had earlier, sorry, I have lots of legal texts, and they are different laws. Is this a similar data set you had in mind?
So I was thinking, since we want to maximize the distance between the lectures, let's say, if the dataset contains similar topics, similar tokens, that would probably not work fine, I would assume, but just a guess.
Yeah, but my expectation would be that the model learns to put similar but not identical text further apart. So it would know how to separate housing bills from cybersecurity bills.
Yeah.
So the distance would increase, and now it's a question of whether do you want that or not. But if your data set is biased towards a certain domain, for example, legal text, then the distance between these embeddings would increase. Usually, however, this is what we want.
But how would you pick a negative sample in that case?
Yeah, so for me, a negative sample would be the cybersecurity bill when I'm talking about legal bills, whatever, housing bills.
Right, but then you need a data set with that too.
Sure. Yeah, like it's like a zoom level depending on where you zoom in. And if you zoom in so far that you actually want all of them to be similar, for example, if you have one long thesis and you don't want any differences between them, then it could become harder. Another thing I had in mind, if your actual text isn't that coherent, so if you have news headlines or like the first page of a newspaper as the text, where there's different news articles in the same text snippet, then you would confuse the heck out of the model.
Indeed. And this would be something that one would ideally need to check beforehand. This like the question of how can you get to a good data set is of course a universal one and not one that is only like constrained to this triplet learning approach. But when you deal with this kind of strategy, I feel like there are many different approaches you could take. For example, and I think like Fabian, you suggested this either explicitly or implicitly, that if you have like a training data set with a high degree of homogeneity, where like all your articles are very, very similar, or all your documents are very, very, very similar, then you could augment your data set by downloading like another text corpus. For example, if you're in this legal domain, you could download like a data set about, for example, natural sciences or something like this, and then you could use them as negatives. The problem with this is, of course, that then your network does not necessarily learn how to distinguish between legal texts that much, but it learns to distinguish between legal texts and non-legal texts. And this is like a very complicated problem to solve. And this is why I've already taken one of the cards from our discussion session later on and put it onto the board right now here. Within this domain of triplet learning, there's this concept of hard and semi-hard mining. And what this means is that you try to find a good balance for how hard it is for the network to distinguish between anchor, positive, and negative. For example, let's say in this legal domain, maybe you want to distinguish between two very similar legal domains that are nevertheless distinguished from one another because of some historical reason or technical reason in the legal domain. Then you want to find the cases that are, okay, no, let's illustrate this. Because like your model is starting out with a certain knowledge about the world, right? It's starting as a general purpose natural language processing model, right? And maybe in the beginning, between these two legal domains, maybe it already represents some of the samples from domain 1, this is domain 1, close together. But it also represents some of the samples from domain 2 intermixed with this. And what you want to do then is you want to find the examples here which are the most confusing to the model. So this one, for example, would be one. And you want to like draw an arbitrary line between these two and say the ones that are the most confusing for the model are the hard examples, and the one less confusing for the model are the easier examples. And so you want to find a balance where you, when you select the anchor and the positive and the negative, you want to balance it out so that the model maybe sees more easy examples in the beginning, and it sees harder and harder examples later on. And this is like semi-hard mining and hard mining in the context of triplet learning. And how you can do this is you can just, like, even before training, you generate all the embeddings for all the samples that you want to feed into the network, and then you generate your data set based on the distance that you start with, or the embedding distance that you start with. And this could be a possibility. This would also be relevant for example, and this might be the case for your company if you want to build a chatbot. Maybe you have like a large collection of bills or invoices, right? And you want to build a neural network, or like you want to build a RAG system that can work with all the internal documents that you have, but you don't necessarily, or in this case, you can't take one paragraph from a bill document and connect it to the next paragraph of the same bill document, because you have a lot of similar paragraphs between all your bill documents, right? And this would be a case where you can do this semi-hard mining, for example, where then the model needs to figure out some certain aspects within a bill. For example, that one bill was about like an order that you had about a certain item or something like this. Yeah. Maybe like one question again to the audience then. What happens if you have a data set that just contains, let's visualize this again. It just contains a collection of paragraphs. It doesn't contain any paragraphs from like documents or something like this. It just contains paragraphs. What happens then?
Magic.
Let's say we only have this, we only have text. Can we do triplet mining with this?
Just from my understanding, like for each row, there is actually a full paragraph of text in there, right?
Yes, yes.
Okay. So if I were to assume that each row is sufficiently distinct for my use case, then I could just use any other row as a negative. However, because I mean, it depends on where you cut in that one Wikipedia article about Google Translate. So I would say it's not an immediate failure. It might get harder depending on your data set, but you could still train a model. For example, like if one paragraph is just about the history of Google Translate, and then the next is about the technical implementation of Google Translate, then you have two distinct articles and two distinct rows, and you can use the second one as the negative. However, if it's chunked across domain-specific paragraphs, then you would get out garbage.
Yes, exactly. And like this is what I wanted to get to with this question. Like if you don't, if you do not know if your paragraphs have a connection to one another, and if you do not know, if you don't have like an overarching structure where it can give you the quote unquote ground truth if something belongs into the same quote-unquote category, or if something is related in this anchor positive relationship to one another, then using this technique is not promising in order to achieve this goal. So we can only do this if we have a certain relationship between paragraphs. And this relationship could be that we extracted the paragraphs from the same document, for example, or this relationship could be that it's from the same class of document, for example. If we could also do this modeling task by just putting together paragraphs from two billing documents and then contrasting them with a paragraph from a document about like HR processes or something like this. But this also illustrates like how flexible the strategy is, and that you don't necessarily need to, or like that you can like superimpose a certain structure in the way that you think about a certain problem, and you can use this concept of the structure in order to then select the positive, the anchor, and the negative. So in our example here, we do this on the level of articles. We assume that every article is distinct from one another and that only a relationship between the paragraphs within an article exists. And of course, this is not true, right? Because here we have some articles about Google Translate, and then maybe we encounter another article about Google image search or something like this. And they might be quite similar because it's all about Google and maybe there's some redundant information in it. And therefore, these two articles are not completely distinct from one another, but they share a certain relationship. And we don't capture this with this approach, right? Because we act like every paragraph from one Wikipedia article is different from a paragraph from another Wikipedia article. And so we just like here basically recreate the structure in which people have created Wikipedia articles. One strategy to augment our dataset, for example, would be to look for hyperlinks within one Wikipedia article to another Wikipedia article and say, okay, so if there's a hyperlink, for example, between Google Translate and Google as the corporation, then we say, okay, so maybe these two are more related to one another than not. And then we could use this as an indicator for either like a hard example, or we could use this to say, okay, so they most likely belong to the same family, and so we don't sample as a negative from the related article. But because our dataset doesn't have information about this, I wasn't able to use this. But this would be like an approach to solve this homogeneity, heterogeneity problem within our dataset. Yeah, cool. Thanks a lot. I think we can just go through the training objective and the results still here, and then we can take our lunch break. So this is the second hard part of today, and it's not as hard as how the encoder architecture works. So this is a mathematical formulation of our loss function that we will be using to train our model. Remember, the loss function is basically like this translation step between formulation of our objective in the real world and a mathematical formulation of this. And if you're familiar with mathematical formulas, then you will see immediately that this is basically just a Euclidean distance function here. What does Euclidean distance mean? It just means the direct line between 2 points is Euclidean distance. But because we are operating within highly dimensional vector spaces, it's not like a 3D distance, but it's a ND distance, so n-dimensional distance. And here the f just says this was put through the BERT model. This is the output of the BERT model. And here it's just the anchor minus the positive, so the distance between the two, and then normalize so that we don't get a negative value here. And then here, the distance between the anchor and the negative, and this gets subtracted from one another. And this basically means if the distance between the anchor and the positive is lower than the distance between the anchor and the negative, we get a lower number. And we add an alpha parameter here, and this is a margin parameter. And this margin parameter is necessary because if the network is very good at distinguishing anchor and positive from anchor and negative, then the loss will be always 0. And this is bad because then the network doesn't learn anything. And so in order to keep the network on its toes, we always add this margin parameter alpha here. And this will come back later. So I will ask you a question about this later. So this is the role that the margin parameter here plays. But for this triplet learning, and actually I'm also using this exact definition of the Euclidean distance in order to calculate the distance between vectors, we just use this Euclidean distance function. If you would use this network within the context of a RAG system, you would need to watch out here, because if you use cosine similarity for your vector database to calculate the relatedness of two vectors to one another, then you would need to use cosine distance here and not Euclidean distance, because there are two different ways of calculating the distance between vectors. Yes. Okay. But that's the loss function that we will be using. And I will show you the way I implemented this later on. And hopefully the result then will be that we get a BERT model after training that can project certain topics into discrete embedding domains or like regions in its embedding space, to model this relationship between different topics from Wikipedia articles. To, for example, say, topics in computer science are related and topics from biology are related, and this is the way they are related to one another. Cool. And I think it's quite nice. It's 11:58, and I would say it's a perfect time to take a lunch break. After the lunch break, we will actually look at the implementation that I did, and we will look through our code. We will just do a code deep dive. Then I can show you something about the training process and show you some results. And then we can have a discussion in the end. Yeah, cool. Thanks a lot. I don't think we will take longer than 3 o'clock today, probably. And thanks a lot for sticking around, and see you again at 13.
See you later.